All right, so continuing our Lecture 2 series, I want to look at another interesting theorem with you. This is called the Generalized Cauchy Integral Formula, as if the Cauchy Integral Formula wasn't amazing enough. So same setup, suppose f is analytic inside and on a simple closed contour C, positive orientation. By the way, orientation isn't a huge deal because we know how to switch it. Then f has derivatives of all orders at all points z naught inside C with, and I thought I would write out the equation for you. So here's how it goes. If you want to know what the nth derivative of f at z naught is, well, it's equal to n factorial over 2 pi I times the integral along C of f of z over z minus z naught to the n plus 1 dz. And just to be clear here, my n could be 0, and in that case we're back to the Cauchy integral formula, or 1 or 2, so on and so forth. And I think you know this already, but let me move this down slightly. When I write f, the 0 with derivative of f, that's just f, and of course 0 factorial, we agree, is 1, just to make life easy on ourselves. Okay, so this is a really wonderful generalization, or as your book says, extension of the Cauchy integral formula. It takes just a moment to swallow it. So really not much is changing. The difference is now instead of having z minus z naught to the 1 power, we've got it to the n plus 1 power, and whenever you see that, then you can work out the integral. So let's rewrite this in terms of just the integral. So we'll say equivalently, the integral along C of f of z over z minus z naught to the n plus 1 dz is equal to 2 pi I times the nth derivative of f evaluated at z naught divided by n factorial. So that's how you can generalize the Cauchy integral formula. So I thought we'd dive in and do a couple of examples with you. And I thought we would do an example that sort of completely captures the very first example that I did with you when we started talking about contour integrals of complex functions. So here we go. Example number 1. So I want to let z naught be an interior point for any positively oriented simple closed contour C. All right, and so whoops, that's supposed to be contour. Okay, so I want to do 2 different examples with you, but first let's draw a picture. Whoops, I struggle to, there we go, draw my curves. So here's my C, here's my Z naught, and the first example that I want to do is the integral over C of the very first problem we did, dz over z minus z naught. And if you recall, we had a specific C. Our C was the unit circle. I'm saying, by the way, you can do this for any simple closed contour C. And when we worked it out over the unit circle, we got 2 pi I. So let's see if we can work this one out and get the same thing over any simple closed contour C. Well, the way to view it is to realize that what you want is to think about this denominator, z minus z naught, to the n plus 1. So I've got a 1 sitting here, so this is really to the 0 plus 1. So I'm going to rewrite that so we can see it. So this is dz over z minus z naught to the 0 plus 1. That means my n is just 0. So by the generalized Cauchy integral formula, this is 2 pi I, the 0th derivative of f evaluated at 1, all over 0 factorial. I forgot to tell you what f is. Take a moment and see if you can see it yourself. What's f? Right? F of z is just 1. It's just the top. This is 1 times dz. So this is just the 0th derivative of 1. Well, that's just 1. So this is just 2 pi I, exactly like we got before. Go back, pause the video, go back, look at your notes. When we worked this out, we actually came up with a parameterization for the contour, and we plugged it in and we worked it out. And it wasn't hard, but it took a little bit of work. Whereas now that we have this generalization of Cauchy's integral formula, it's relatively straightforward. Okay, so let's do another example. So what if we change the same situation, but what if we have the integral over the same c now, any simple closed curve positively oriented, and what if I have dz over z minus z naught to the n, and I want to assume here that n is greater than or equal to 2. We already did n equals 1. Well, the key, again, is how you view this. So we're going to write this as 1 over z minus z naught to the n minus 1 plus 1 dz. And so the point is, this is my f of z, and I also notice the n minus 1, that's the key. This n minus 1 is going to be the key. That's actually playing the role of my n in the Cauchy integral formula. And so this is exactly 2 pi I over n minus 1 factorial times the n minus 1 derivative of f, plug in z naught. But again, my f of z is just a constant, and if you take the first derivative or any more, then that's going to be 0. And so the point is, n minus 1, the n is at least 2. So we're taking at least the first derivative. So we're guaranteed that this guy, that was a very bad wiggly, let's try again. This guy, still not very good, is just 0. So the point is, the whole thing is 0. And we did an example very similar to this way back at the beginning as well. Let's do another example or two of this formula, and then we'll go on and see some implications of it. So that was example number 1. It had 2 parts, A and B. Let's do example number 2 now. And so this time, I want to work out the integral over c of e to the 2z over z to the 4th dz. And here my c is going to equal the unit circle, so centered at 0 with radius 1, and of course we're going to go positively oriented. All right, so I look at this problem, and I need to identify f of z, and then I have to be able to think about this in the right way. So I'm going to go ahead and say, look, let's label this integral star so we can come back to it, and we're going to let f of z be just e to the 2z. Okay? And then I can say, well, star is equal to the integral over c of f of z. And then I want to write this as z minus 0. Yeah, it's 4, but you want to write it as something plus 1. So 4 is 3 plus 1. And now you know what your n is. N is exactly 3. I should put a dz on the end. N is 3. And so I'm more or less done. This is just 2 pi I times the third derivative of f, plug in 0, over 3 factorial. Let's think through the third derivative together. Maybe we'll just write it down over here. Each time you take a derivative, you kick out a 2, so this is just 8 e to the 2z. That's the third derivative of f. Plug in 0, and you just get out 8. So I'm going to get a 16 pi I over 6. And this, of course, cancels down to 8 pi I over 3. And I'm done. That's example number 2. All about seeing these integrals in the right way, and then you apply the theorem. I'll do one more with you. So number 3, think I can squeeze this in on the rest of this page. So I'm just going to draw a picture of my curve. I don't feel like describing it. It's too much work. So let's see. I want 1 to be inside of it. So something like this. Hopefully my iPad will do this. I want an ellipse. Oh, perfect. Man, first try. So here's an ellipse. I'm not saying it's centered at 1 necessarily, but 1 is inside of it. We're going to do positive orientation. Here's C. And I want us to work out the integral over C of z to the 10th over z minus 1 to the 11th dz. I would challenge you to pause the video, work it out, and then you can watch it and see if your answer agrees with mine. So I'm going to begin by saying let f of z be z to the 10th. I've not been pointing this out in the last 2 problems, but of course, right, of course, I'm making sure that my f is analytic inside and on C. And I don't feel like scrolling up, but all the examples that I worked out, that has been the case, and so that's why this works. So I've got f of z is z to the 10th, and now I'm going to rewrite my problem. I think I'll just put an arrow down here, and I can write this as the integral over c of f of z, z minus 1. 1 is inside my curve, that's good, to the 10 plus 1. Okay, so by the generalized Cauchy integral theorem, this is 2 pi I over 10 factorial times the 10th derivative of f at 1. Now, I don't really want to work out the 10th derivative, but it's not that hard to see how it goes. When you take a derivative, first derivative is 10 z to the 9th, and you're just going to keep kicking out. So 10 times 9 times 8 times 7, blah, 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 blah. If you go too far, you're going to get 0. Thankfully, when we take the 10 derivatives, we're going to be left with a constant, and the constant is going to be 10 factorial. So this is 2 pi I times 10 factorial over 10 factorial, which is exactly 2 pi I. All right, so we'll stop this video here, and then in the next one, we'll look at a couple of implications, and we'll go from there.